Introduction to three-phase systems. In this presentation, we're going to be looking at a review of basic single-phase generation and how that occurs, how three-phase is generated, the advantages of three-phase represented with phasors, and finally, the three-phase system configurations that we can expect to see. Single-phase generation is accomplished through a conductor that is rotated in a circle past a magnetic field. Now, this is a very basic representation of what's occurring, and it is very much dependent on understanding that the voltage peak value will be reached when we have conductors that are crossing the magnetic lines of flux at a 90-degree angle. So that would be up here and down here. When the conductors are here, it means that they are actually running parallel to the lines of flux. And because of that, there will be 0 volts produced. And that's why we get this classic sine wave with one positive alternation, one negative alternation, and a point where the current and voltage and power of the system reaches 0. Common voltages that we see in single phase would be 120 volt AC or the 120/240 volt system that's very common in residential applications. In a single phase generator or alternator, there is one winding in the stator in order to provide us with that one single phase. In a three-phase generator or alternator, there are 3 windings in the stator. Notice their position. They are equally spaced from one another in the stator of the machine. And because it's a circle and there are 3 of them, it means that they each have a physical rotational separation of 120 degrees. In a standard 3-phase generator, we have these 3 individual windings that are all built into the same machine, thereby providing us with 3 independent phases of alternating current. If we look at a 3-phase generator, there are going to be 3 individual windings. And if we look at each one individually, we can then start seeing where the sine waves are being generated. If we look at A phase here, this would show that we have an independent voltage that's being generated on this one individual winding. Now, of course, there is no other winding that's going to reach its peak value at exactly the same point because no 2 windings will be passing the main face of the poles at exactly the same moment. There's a 120-degree separation between the windings. If we look at the B phase winding, or phase 2 in this system, you'll notice that the sine wave happens to be offset from the previous one that we looked at. The first one was in a slightly different position, and that's because this winding is 120 degrees separated from the A phase winding, which is right here. Finally, if we look at the third winding, we'll call this C phase, this one too will be offset from the preceding 2. And so what we have is 3 individual single phases. And these 3 individual single phases we typically show on a single sine wave graph. And the reason for that is because all of them are being generated from the same physical machine. So notice that they are independent and they are not in some way, shape, or form combining or melding together. They are 3 distinct individual phases that happen to be offset by 120 degrees due to their physical mount inside the stator of the generator. This is an easier graph to view and see the difference. It is a uniform separation where A, B, and C reach their peak values 120 degrees apart from one another. Just like in single phase, there is relative motion. And since those 3 windings are physically separated by 120 degrees, they each reach their peak value at different times, 120 degrees apart. This is another animation to show the concept. Now on this animation, we do also have another connection that's down below, and it's labeled neutral. And we'll discuss what this is and how it functions in a later presentation. So on a single phase AC generator, you would notice that there would be a definite pull and push on the single phase. Now this would be an extremely low frequency that we are watching here on that single phase AC generator. But what's important to understand is that the load would be left with zero power when the direction of current reverses in the middle of a sine wave cycle. And what I mean is that 0 point right there on the sine wave. Zero voltage, zero current means zero power to our load. If we were to contrast that against a three-phase AC generator, notice that the push and the pull is not happening at the same time for each phase. And this is due to the sine wave in each phase reaching its peak value at a different time, 120 degrees apart. So when contrasting a three-phase source to a single-phase source, a three-phase load would never be without voltage, current, or power at any point, because it would always have one of the independent phases providing a maximum value of current. And here's a three-phase AC load. It's an interesting animation to show what's happening with the actual current at each point. And we'll get into more depth as to what is occurring at that center tie point where we see all three of these connections together. Three-phase systems are more efficient than single-phase systems for much the reasons that we just looked at. And due to this, motors can be constructed much smaller when they are three-phase. A half-horsepower single-phase motor will be immensely larger than a half-horsepower three-phase motor. In addition to this, single-phase motors are only built up to a certain size. It is very rare to find a single-phase motor that exceeds 5 horsepower, although they are built up to 10 horsepower, whereas three-phase motors are built into the hundreds of horsepower. Motors will also run smoother on more phases, and that again is because of three-phase not having a point where 0 volts and 0 power is being applied. So by contrast, a half-horsepower single-phase motor would be rough and choppy in its rotation when compared to a three-phase motor. Less copper is required to supply loads. Well, let's take an example. This is a 10,000 watt electric heater rated 240 volts single phase. Each of those windings or heating elements is rated for 240 volts, so we've put them in parallel, ensuring that each get their rated voltage. 10,000 watts divided by 240 volts would then mean that we have 41.6 amps that is flowing to and from the heater. If we took that to the Canadian Electrical Code, just as a baseline wire size, we would get a two number 8s copper conductors if installed in conduit. Now, what if we were to take this same heater and instead run three-phase to it? Well, in three-phase, we would actually have to connect those individual heating elements in a slightly different configuration, which we are going to go into in a later presentation. We actually have this connected in Delta. We are going to provide 240 volt three-phase to this heater. And when we do our calculation for the current, we're actually going to get 24 amps. The exact same amount of heat is going to be generated. However, now we have run much smaller conductors, and although I agree we've run one more conductor, the total amount of copper that we have used is far less and is going to be cheaper. When we look at phasors for a three-phase system, the most common application and common diagram that we're going to see is with A, B, and C labeled for the RMS voltage at 0, 240, and 120 degrees. And that is because the rotation of phasors on a Cartesian plane is always in a counterclockwise direction. There will be more details on this, as it will be a little bit different when we look at different configurations of three-phase. Three-phase loads and sources come in two distinct configurations, Y and delta. These two names are based on what they look like visually when we connect them together. We can have three-phase sources that are either Y or delta. Y looking like the letter Y, or sometimes referred to as a star connection. Delta looking like a triangle. Three-phase sources would typically be things like alternators and transformers. On the other hand, we also have three-phase loads. They again come in the same configuration of Y or delta. Now, this particular diagram, you'll notice, is positioned slightly different so that the star is facing up, and so is the point of the delta connected load. This is not of extreme importance, but it is something that you would see in most illustrations to distinguish the difference between a source and a load. Loads are often three-phase, being motors or three-phase heaters.